As 4.3 million people die each year because of bad air quality, air quality becomes one of the most important aspects of people's lives, and many people do not actively take measures to improve the air quality in their homes. The indoor air quality can become polluted from a number of anthropogenic or natural sources, which can cause an increase in carbon monoxide, carbon dioxide, nitrogen dioxide, sulphur dioxide, ozone, and volatile organic compounds, all of which at high concentrations can cause major harm to animals and babies in particular, as their lungs are still developing. Low pollution levels can cause sick building syndrome, which causes a feeling of ill health and a decrease in productivity. Knowing this information, an air quality monitoring and purifying tool is of utmost requirement. Current air quality purifiers make use of filters. These require human interaction to be replaced every certain period of time. However, people are not aware of this or sometimes forget. Thus, a tool that does not require human interaction is of utmost requirement. This tool makes use of an ESP8266 microcontroller and an electromechanical linear actuator that can automatically open and close a window depending on the level of air quality and temperature without the need for human interaction. But also this tool makes use of a Grove air quality gas sensor that makes use of an MP503 sensor, a Grove CO2 and temperature and humidity sensor that makes use of the SCD30 sensor, and a Grove multi-channel sensor that we are using to measure carbon monoxide. However, in future, sensors can be added or removed depending on the requirement of the user. And this allows us to measure air quality in real time and identify when the air quality starts to become polluted and open a window as required. This data is also displayed clearly on an LED strip, with green displaying good air quality, yellow displaying low pollution, and red displaying high pollution. When the air quality starts to become low, the user can clearly see that the air quality has gotten low using the LED strip. Google Assistant has been implemented in the project to allow the user to easily identify what the temperature, humidity, and air quality is in real time anywhere around the world. A live dashboard has been created that depicts the important information about the air quality in an easy to understand manner. The data is sent to the cloud, which allows a user to view historical data from any point since the device started to transmit data. Using the hardware that I just talked about, here you can see the SCD30, which I'm using to measure temperature and humidity, the air quality sensor, which is highly sensitive to smoke and alcohol, and the multi-channel sensor, which we're using to measure carbon monoxide. As just explained, the air quality sensor is highly sensitive to alcohol and smoke. The LED strip is connected to the air quality sensor. When the air quality sensor detects bad air quality, the LED strip will start going sequentially from green to yellow to red. Red determines high pollution, yellow determines low pollution, and green determines fresh air. When the air quality sensor detects bad air quality, it will signal the linear actuator to open the window. As soon as it detects good air quality, it will signal the linear actuator to automatically close the window. We can see this in action here. Here we have some perfume which contains high concentrations of alcohol. When the bottle is shaken and some is put in the cap and we put it on top of the sensor to simulate bad air quality, the sensor automatically jumps to red, simulating high pollution. The linear actuator opens, and when we remove the cap, it goes to yellow, and the linear actuator carries on opening because it's detecting low pollution. However, when it detects green air quality, the linear actuator will begin to close because the air quality is green and the window is no longer needed to be opened. The linear actuator is also affected by temperature, not only air quality. So when the temperature reaches a level that is considered uncomfortable, so 28 degrees, the linear actuator should automatically open. We can demonstrate this by covering the sensor. Here you can see that the temperature is 27.37 degrees. When covering the sensor, the numbers are quickly increasing to 27.41, 44 degrees, for example. Now when the temperature reaches 28 degrees, the window should automatically open. Here you can see the temperature has reached 28 degrees. When 28 degrees has been reached, the window linear actuator is automatically opening. However, the sensor now has been, the hand has been removed, and the sensor now has detected that the temperature is going down. So when the temperature goes below 28 degrees, so say 27 degrees, the window will automatically close. You can see this now. Here you can see that the temperature has reached below 27 degrees. The window is automatically starting to go down and close. This now simulates that the window actuator is closing. Here you can see the dashboard running on a public link that can be viewed anywhere around the world. The dashboard updates in real time every 4 seconds, and the data is automatically stored in the cloud. As the data is stored in the cloud, the dashboard allows for historical analysis of the data to further understand the trends. By using the date picker, we are able to pick whichever date we want to view these trends. We can pick it from a time period of a week, month, year, or even since the day the device started to transmit data. Either way, the dashboard clearly shows air quality, temperature, humidity, and carbon monoxide. However, similar to the hardware where sensors can be easily added and removed, new graphs can be added and removed detailing different substances depending on the user's needs. As mentioned previously, the dashboard is useful when viewing historical data. A simple example of this is by using the date range navigator and jumping back to the 12th of June. You can clearly see that we are viewing historical data from the 12th of June midnight till the 12th of June at 11:59:59 seconds. The microcontroller was left running for 24 hours, and some important pieces of data can be easily seen on the dashboard. Mainly, it is clear that here there's no spikes of bad air quality shown. Furthermore, when analysing the graph for the temperature, the highest average temperature reached was 31 degrees, and the lowest being around 21 degrees. But most of all, the graphs clearly show the robustness of the device, where it was able to continuously record data for 24 hours straight without any errors or dropping in connection. This demonstration will show the Google Assistant in action. As mentioned previously, the Google Assistant is able to capture data in real time anywhere around the world for temperature, humidity, and air quality. Here I'm screen sharing my phone with data turned on to demonstrate this functionality of the Google Assistant. Talk to Hani Katab.
Okay, let's get the test version of Hani Katab.
Hello, how can I help you?
I'll first start by asking Google Assistant what the current temperature is. Google Assistant should be reading this number. What is my temperature?
The temperature right now is 27.01 degrees centigrade.
Here you can clearly see that the temperature was correct, and it is 27.01 degrees. I would now start by asking Google Assistant what the current air quality is. It should say it's fresh and clean because the air quality is in the green zone. What is my air quality?
Your air quality is clean and fresh.
I'll now start by asking Google Assistant what the humidity is. It should say 41.17%. What is my humidity?
Your humidity is 41.12%.
And here you can see that at the time it was 41.12, it's just changed now. But this demonstration clearly shows that Google Assistant can work anywhere around the world and that the person can view the temperature, humidity and air quality in real time without any problems. Finally, it's clear that the device achieves the main aim of the project, which is to develop an IoT platform for measuring and reducing air pollutants in indoor environments to improve health and overall well-being. The linear actuator directly helps to reduce air pollutants and temperature when required, and the Google Assistant LED strip and dashboard allow the user to better understand their air quality in real time to promote behavioural changes, further achieving the aim. Furthermore, all the project objectives have been met, including a thorough testing of the device to ensure its safety and accuracy. This can be detailed in the testing strategy section of the dissertation. Thank you very much for viewing my video and have a good day.